Today we're going to continue with section 10.1, and for the notes today we're just going to look at a couple more examples. Again, all the definitions were in the first day of notes. If we look at this diagram, what we see is segment P or segment SR that is tangent to both circle P and circle Q. From the 10.1 day 1 notes, we have a rule that says when a line is tangent to a circle, it is perpendicular at the point of tangency. So I know that there is a right angle here, and a right angle here. We also know that these are circles. So over here we have some information about some of the lengths. The length of QT is 6. And if we notice, QT is a radius of circle Q. So we also know Q to any other point on the circle is 6. We're told TR is 8 and PR is 30. So PR is this whole length here is 30. The diagram that we have with the circles, we can actually take out of the circles at some point here. Things to kind of keep in mind as you're doing circle problems are things like every radius of a circle has the same length, which may seem obvious, but is something to kind of keep in mind as you go. Sometimes it's helpful to draw a radius to an important point if you don't have enough information. Also, once you have everything marked in your diagram, sometimes you can just remove the circles. So if I go down here and copy these triangles without the circles, and I'm going to kind of change the direction a little bit, what we see is that this is a diagram we saw a lot earlier in the year. We have right angle at S, we have point P, we have point R, and then we also have a right angle at T, and we know that TR is 8 and TQ is 6. And if we look at this right triangle, 6, 8, 10 is one of our special Pythagorean triples. We also know PR was 30, so PQ would be 20. But this is a diagram we saw a lot in the similar triangles chapter, where you have a triangle with a line that's parallel to one side. These two lines have to be parallel because they're both perpendicular to SR. So if these are parallel, we know that this top triangle, RTQ, is similar to the big triangle, RSP. Which means the corresponding sides are in proportion. And if we look at the sides, we want to find PQ. So that was 30 minus 10 is 20. We want to find PS. PS is this side of the bigger triangle. So we need to find the scale factors of the small triangle to the large triangle, which we have from the 10 and the 30. 10 to 30 is 1 to 3. Corresponding sides are in proportion. TQ, the 6, is the side that corresponds to SP. So I can solve this proportion. I can use cross products. 1 times SP equals 3 times 6. So SP is, or PS is 18. Then I also want to find ST, and you have a couple options in this case. We could do Pythagorean theorem to find SR. We could use the similar triangles to find SR. We can also use triangle proportionality theorem. Triangle proportionality theorem says when this line is parallel to the third side, it divides the other two sides proportionally. 10 is to 20 as 8 is to ST, or 1 is to 2 as 8 is to ST, which means 2 times 8 equals 1 times ST. The length of ST is 16. In this diagram, we have segment JK that is tangent to circle P and circle Q, which means that when we draw in the radius to each of those points of tangency, we're going to have a perpendicular. So if I draw in P to J, that's 90. And if I draw in Q to K, that's 90. What we want to find is the length of JK. And there's a hint here. What kind of quadrilateral is JPQK? JPQK, we see the two right angles, which means two lines that are perpendicular to the same line have to be parallel to each other. And this is a quadrilateral that has two sides that are parallel. In other words, it's a trapezoid. And we also know some lengths here. We know P to the edge of the circle here is 11. That's the radius of circle P, which means that this segment over here is also 11. We know 3 to the edge of the circle here, Q to the edge of the circle is 3. So the radius here is also 3. I'm going to draw this quadrilateral out on the side. It's a trapezoid with two right angles, and it may not be drawn well to scale. We have J with a right angle, excuse my drawing. We have K with a right angle. We have Q, we have P. J to P is 11, K to Q is 3, and if we add this up, 11 plus 3 plus 3, this length is 17. When we have trapezoids, sometimes it's helpful to break them into a right triangle or multiple right triangles and a rectangle. In this case, if I draw a perpendicular across here, what I get is a rectangle on the top and a right triangle at the bottom. Now that rectangle, K to Q is 3, so it's also 3 on this side. And then that 3 is part of this 11, so from my perpendicular down has to be 8. This right triangle now has a leg that's 8 and a hypotenuse that's 17. You can either use Pythagorean theorem or recognize the Pythagorean triple, 8, 15, 17. We can use the leg and the hypotenuse to find this leg. Now we look at the rectangle. Rectangle opposite sides are congruent, so JK is also 15. Again, the hints are draw in a radius to any important point. Remember, every radius of a circle is congruent. And sometimes it's helpful to draw the figure outside of the circles once you have as much labeled as you can. The last two problems are the types of problems that we call walk-around problems. And so these are helpful when we have tangents to a circle that form a polygon, like the triangle ABC here, where side AB, side BC, and side AC are all tangent. If the lengths of the sides of the polygon are known, then the lengths of the tangent segments can be found using algebra. And we call these a walk-around problem, and you'll see why. Let's move down. So here we have this fence where we're given that A to B is 20, B to C is 32, and A to C is 26. So we know all three side lengths for this triangle. We want to find the lengths of the tangent segments. In order to do this, we're going to use the property from the other day, which said that when you have two tangent segments drawn from a point outside of a circle, they're congruent. So AP and AM are congruent, MC and NC are congruent, and PB and BN are congruent. I'm going to pick any segment in this triangle and call it X. Let's start up here. If A to P is X, A to M is also X. And what we're going to do here is we're going to walk around the triangle and try to write everything in terms of X. So A to M is X, A to C is 26. So M to C would be 26 minus X. I'm going to take away that top part. And M to C is congruent to N to C, so this length down here is also 26 minus X. And then you have a choice. You can keep walking around in this direction, or what might be easier right now is go back up to X and walk around in the other direction. A to P is X, so P to B is the 20, take away X. And B to N is congruent to B to P. This is also 20 minus X. And what we should end up with is a side where we can write an equation. On this side, we have 20 minus X, and 26 minus X has to add up to our total length of 32. So I'm going to combine some like terms, 20 plus 26, negative X and negative X, 32. Let's subtract the 46 from both sides, negative 14. And when I divide both sides by negative 2, I get that X equals 7. So when I go back to this diagram, my X is 7, which means AP and AM both have lengths of 7. PB and BN are both 20 minus x. 20 minus 7 is 13. And then my last two segments, MC and NC, are both 26 minus x. 26 minus 7 is 19. The last problem is another walk-around problem, but in this case, it's a little bit different because we can never actually find some of these individual lengths, and that's because it's a quadrilateral. So we're given that JK is 22, KL is 15, and LM is 13. What we want to do is find the length of the fourth side, JM. Again, we know that any two tangents from a point to a circle are congruent. So we have 4 sets of congruent segments. Sorry, these two. And then these last two. You can pick any one of these 4 segments to call x. So say we start up here. If this is x, it's also x on this side. So k to the point of tangency is going to be the 22 of jk minus the x. And k to this point of tangency is congruent. So this is also 22 minus x. Now you need to be careful. To get the distance from this point to L, we're going to take the whole segment length, which is 15, and we're going to subtract the top part. When you do that, you need to make sure you distribute your subtraction. 15 minus 22 is negative 7, and then I have to subtract negative x, which makes it plus x. It's negative 7 plus x or x minus 7, either way. And this segment down here would be the same. Now we need to find from the point of tangency over to M. So we're going to take the 13 from that side and again subtract the entire expression, negative 7 plus x. 13 minus negative 7 is 20 minus x. So this segment here is 20 minus x, and it's also 20 minus x over here. In this problem, we want to find JM. There is no way to figure out what x is. There are several different situations that would fit with this problem for as far as different values of x. What we want to find is JM. JM is these two segments added together. So I'm going to add x plus the 20 minus x. When I do that, the x and the negative x cancel out, and I'm able to find the length of JM. For today, make sure that at the end of class, you complete the attendance form that's at the top of the classwork section, and that you put any questions you have in the lesson in there. I'm also on the Google Meet for anyone who would like to ask questions during class.